rheostat structures. The electronegativity of an atom is something that was devised by Linus Pauling in order to determine the ability of an atom to draw electrons to itself within a bond. Shown here is a table of the various electronegativity values for the main group elements, or some of the main group elements, and in this case you can see that fluorine has the highest electronegativity value of 3.98. Electronegativities decrease as you go from right to left within a period and decrease as you go down a group. Shown here is the electronegativities of the elements in the periodic table, showing the overall trends. You can see that the highest electronegativity values are for the nonmetals in the top right-hand corner of the periodic table, and down in the lower left-hand corner is the lowest electronegativity values. These are exactly inversely related to the size of the atoms and is due to the same basic properties of formal nuclear charge, or the effective nuclear charge, and the shells that are involved in the valence, creating the valence shell. There are three basic types of bonds that we will be considering in this section. We will be talking about nonpolar covalent bonds, which is a complete sharing of a pair of electrons. In other words, the two atoms involved have the same electronegativity value, or virtually the same electronegativity value. We can, on the other end of the scale, are the so-called ionic bonds, in which the electrons reside almost completely on one of the atoms, forming an anion, in this case the fluoride anion, and the other atom involved, in this case the lithium cation, basically is stripped of its valence electrons. So that there is little or no sharing of electron pairs at all. The main force of attraction between these two atoms is purely an electrostatic, or opposite charges cause the attraction. So the electronegativity values, or the difference in the electronegativity values between the two atoms, can be used to predict which one of these two extremes will be observed. But of course there are things in between, and we call these polar covalent bonds. In this case, there is an unequal sharing. There is some sharing, much like a nonpolar covalent bond, but there is also a big enough electronegativity difference so that the pair that is shared spends more time with the more electronegative atom. In this case, fluorine is more electronegative than hydrogen, so it has some ionic character. In the case of a chemical bond between hydrogen and fluorine, the difference in electronegativity results in the drawing of electrons towards the fluorines, giving the fluorine atom a partial negative charge. It's not a full-blown 1- charge, but then there's the corresponding partial positive charge. The fraction associated with this overall positive and negative charge is denoted by the Greek letter delta, as shown here. So it turns out then that one end of the molecule is positively charged, the hydrogen end, and one portion of the molecule is equally negatively charged. And so we refer to this as a dipole, or a polar bond, and therefore we have a polar molecule. So to calculate the electronegativity difference, you simply look up the electronegativity values for the two atoms involved. In this case, fluorine being the most electronegative atom, it is then subtracted from hydrogen, which is quite a bit less electronegative, and we come up with a difference of 1.9 electronegativity units, which is a pretty substantial difference in electronegativity. This can be compared to the difference between carbon and hydrogen and a CH bond, which is virtually zero. And so in essence, this would be a nonpolar covalent bond where there is complete sharing. So these are two classic examples of polar covalent bonds and nonpolar bonds. If a molecule contains a polar covalent bond, it potentially could be a polar molecule, and we can then decide upon whether or not this molecule has a directionality associated with the overall distribution of the electron density. In this case, for HF, we can measure this vector quantity fairly easily because there's only one bond and only one direction associated with pulling the electrons towards the fluorine. And so the number associated with the so-called dipole moment is given by the electronegative, or the difference in the charge associated with the two different atoms multiplied by the distance between the two atoms. The further the distance between the different charges has an effect on the overall dipole moment. So longer bonds can end up having a pretty significant effect. The example here, we can symbolically represent this both in terms of the partial charges using the delta positive and delta negative. Again, these are fractions associated with the partial charges. Or we can use a vector arrow with the head of the arrow pointed towards the more electronegative atom and the positive tail being associated with the least electronegative atom, as shown here. We're going to be drawing Lewis-Dot structures, and much like structural formulas, Lewis-Dot structures tell us something about how the atoms are arranged in space, but also give us an idea of the different kinds of electrons that are present in the molecule. So, as you can see here, we have the Lewis-Dot structure, or a Lewis-Dot structure, for the elemental chlorine, or Cl2 molecule. In this case, a single chlorine atom would have 7 valence electrons for a total for 2 chlorines of 14. In this case, then, if 2 of the electrons are shared between the two, we then come up with a situation where both chlorine atoms get to have 8 electrons in its valence shell, which is a noble gas configuration. As shown here in blue, the pair of electrons between the 2 chlorines is a bonding pair of electrons, whereas each chlorine also has pairs of electrons that are not shared, and therefore we refer to these as lone pairs or non-bonding pairs of electrons. In order to draw a Lewis-Dot structure, we have to follow several steps to draw out the bonding pairs and non-bonding pairs of electrons. The first step involves determining the total number of valence electrons within the molecule or ion. The crucial thing is that for positively charged ions, cations, we end up having to then take away the number of electrons associated with the overall charge, whereas anions, we would add additional electrons corresponding to the overall charge. All right, the next step involves drawing a skeleton structure. In this particular case, we would then connect the atoms to one another using a line. Each line that is used to connect the atoms together represents a pair of electrons, a bonding pair of electrons. The crucial thing is to know something about how these atoms are connected. And in this case, usually when you write the formula, the central atom is the least electronegative atom, and then in the case of the more electronegative atoms, these are referred to as terminal. They are on the ends. At this point, then, we are going to take and distribute any remaining electrons not used in forming the skeleton structure and give them to first terminal atoms and then possibly to the central atom. In the case of hydrogen, which is always a terminal atom, it only requires 2 electrons in its valence shell to be like helium. So this is usually satisfied when forming the skeleton structure. However, if the terminal atom is represented by second or third period elements, in those cases we can add up to 8 electrons, and in that case, then that satisfies the outer shell and is sometimes known as the octet rule. If you are short of electrons for any of the atoms at this point, you can then convert any kind of lone pairs on the terminal atoms into shared pairs of electrons between 2 atoms, and this can be done to form both double or possibly triple bonds to then satisfy the octet of not only the terminal atoms but also then the central atom. If there are additional electrons at this point, you then have to be aware that certain atoms can violate the octet rule. This violation of the octet rule only occurs for third period elements, or if they're in periods that are greater than the third period, they can also violate the octet. But the second period elements never violate the octet, and that is an important rule that is never violated. In this slide, we'll go through the process of writing Lewis dot structure for a typical molecule, in this case PCl3. So we're going to follow the process by using this table. Initially, we are going to consider both phosphorus and chlorine. So the number of atoms, we have 1 phosphorus and 3 chlorines. If we look at the electron configuration for both phosphorus and chlorine, we can see that the valence electron configurations, using the abbreviations so that we have the noble gas cores, shows that the phosphorus has a total of 5 valence electrons and the chlorine has 7 valence electrons. This gives us then a total number of electrons of multiplying the number of atoms times the number of valence electrons. In the case of phosphorus, there's only 5. In the case of chlorine, there's 3 times 7, or 21. So we add those together, we come up with the total number of electrons at this stage of 26. At this stage now, we're going to draw the skeleton structure, and so the phosphorus is the central atom, and we're going to connect the 3 chlorines to that central atom, forming bonds. In this case, we have used the 6 electrons to form the bonding pairs of electrons. So we're going to subtract those 6 electrons from the total. There are therefore 20 electrons remaining. Finally, for those remaining electrons, we need to distribute the electrons first to the terminal atoms and then, if necessary, to the central atom. So we're going to give pairs of electrons to the chlorine atoms until we come up with a total of 8 electrons. In this case, we have 3 pairs of electrons that we've added to the chlorine on the left, plus the bonding pair of electrons, which is then a total of 4 pairs, or 8 electrons. We do that likewise for the remaining 2 chlorines. At this stage, we have used 6 times 3, or 18 of the remaining 20 electrons. We see that phosphorus only has a total of 6 electrons around it because of the shared pairs of electrons, and so the remaining 2 electrons can go to the phosphorus, producing the octet for